Welcome back! Today, we've got an incredibly exciting explainer lined up for you. We're diving into a brilliant piece of engineering that literally reimagines one of the oldest inventions in human history, the wheel. More specifically, we're going to look at how a team of researchers figured out a way to make car wheels generate their own power. Why? Well, to help tackle our escalating global fuel crisis. It's this totally fascinating intersection of mechanical design, digital simulation, and green energy. So let's get into it.
I really want you to think about this for a second. What if the wheels on your car actually generated their own power? For over a century now, we've just relied on the traditional setup, right? Combustion engines doing all the heavy lifting. And they don't just push the car forward, they do literally all the electrical work, powering the lights, the ignition, your radio, the whole shebang. But doing all of that wastes a ton of precious fuel. So what if the simple act of rolling down the street could power your vehicle's electronics instead?
To understand why this is such a big deal, let's contrast the old way with the new way. The old way relies on the engine transferring power over a belt to an alternator. Now that sounds fine, but in reality, about 2 to 3% of a vehicle's combustion energy is completely wasted just running that alternator. Doesn't sound like a lot, but in a world facing a severe fuel crisis, that waste adds up tremendously. The new way, the one proposed by this research, is a highly efficient setup where the spinning wheel hub itself harnesses rotational energy and powers the alternator directly.
Here is our roadmap for today. We're going to start with the hidden fuel drain, move through a radical wheel redesign, tackle the weight problem, explore sculpting with software, run a virtual stress test, and finally, look at the future of sustainable wheels. Section 1. The hidden fuel drain.
With our massive global demand for cars driving a severe fuel crisis, honestly, every single drop of fuel saved matters. To solve this, the researchers didn't just take wild guesses. They followed a highly rigorous 5-part methodology. They moved logically from conceiving the initial 3D model right to selecting the perfect materials, defining real-world boundary conditions, structurally optimizing the mass, and finally pushing toward prototype development. This tight methodology was absolutely crucial to ensure the new wheel could harvest energy without ever compromising the driver's safety or the vehicle's performance.
Section 2. A radical wheel redesign. Okay, so to turn an ordinary wheel into a mobile power generator, we have to rethink the physical mechanism. This is definitely not your standard wheel hub. The researchers actually designed a connecting rod and a dual pulley system built directly into the assembly. They nested a belt pulley system right inside the wheel hub to capture rotational energy from the tires. By utilizing that spinning motion, the setup interacts with a magnetic field, using a stator and rotor to generate 12 to 24 volts of 3-phase alternating current, which amazingly is exactly what a vehicle's electrical apparatus needs to run.
But, of course, we hit a massive roadblock. The inciting incident of our story, if you will, is that adding hardware inherently adds weight. Attaching a bulky alternator and a pulley system makes the wheel heavier. And a heavier wheel means more rotational inertia, decreased torque, and ultimately a lower RPM. If the wheel is heavier, the engine just has to work that much harder to turn it in the first place, which entirely defeats the initial goal of saving fuel. It's a real catch-22.
Section 3. Tackling the weight problem. So to offset the added weight of that alternator and those pulleys, the engineering team had to go on a hunt for a material that was incredibly lightweight, yet extraordinarily strong. I mean, they couldn't exactly just hollow out a standard steel wheel and expect it to survive a pothole, right? Instead of standard mild steel, they went with aluminum alloy AZ80. Its composition is fascinating. It's actually 90% magnesium, 8% aluminum, and 0.5% zinc. This specific alloy is an absolute game changer because it delivers a significantly higher yield strength than regular forged steel while remaining astonishingly lightweight.
And the hard data heavily backs up that choice. When we map out stress versus strain, it clearly proves that the yield point for mild steel actually hits before the aluminum's yield point. This gives our AZ80 alloy a vastly superior proportionate limit and a wider plastic area. In plain English, it's just way better equipped to handle the grueling forces of the road without permanently deforming.
Section 4. Sculpting with software.
Now, even with a superior material, the wheel was still carrying too much bulk with that added generator. The solution? Topology optimization. It is this incredibly sophisticated mathematical method used to optimize the distribution of material within a given space. Think of it like a digital sculptor, very carefully chiseling away excess stone.
The engineers used an approach called the solid isotropic material with penalization, or SIMP for short, running it in a software called ANSYS. The software identifies exactly where the wheel experiences low stress, and it literally carves the unneeded metal away in the computer model to drop the weight without sacrificing strength.
To pull this off accurately, you have to break the wheel down into tiny, computable pieces. This is done through a process called hexahedral meshing. The software divided the CAD model using microscopic 3mm elements, resulting in exactly 17,970 distinct nodes and 9,280 elements. Basically, it's like building the wheel out of thousands of tiny digital Lego bricks. Every single one of these interconnected nodes helps the software perfectly map out how physical stresses will ripple through the wheel the moment it hits the pavement.
Section 5. The virtual stress test. Look, it's one thing to make a hollowed-out wheel look cool on a computer screen. It's a whole different ballgame to ensure it can actually survive the brutal forces of a speeding car. The researchers simulated some intense, real-world conditions for their 15-inch wheel. We're talking a 1,000-kilogram car carrying an additional 15-kilogram alternator system. They cranked the virtual speed to 60 kilometers per hour, which translates to over 830 RPMs, and applied a crushing downward normal force of 9,947 newtons. They made absolutely sure this simulation accurately reflected the heavy, punishing burden of a real vehicle in motion.
When we analyzed the resulting heat maps from the finite element analysis, the colors really tell the whole story. The deep blues represent areas of incredibly low stress, dropping all the way down to around 24 pascals. But the bright red zones, those highlight the maximum deformation under heavy pressure. By seeing exactly where those red zones popped up, the engineers knew precisely which parts of the rim they had to leave intact and which blue, low-stress parts they could safely shave away.
And wow, the results of this digital chiseling were staggering. After running the software through 36 separate structural iterations, the engineering team achieved a massive 15% overall mass reduction. They successfully dropped the rim's weight from 4,500 grams down to a super sleek 3,721 grams. They managed to completely offset the weight of the new electrical hardware.
But even more impressive than the weight loss is the safety factor, which stayed locked in at 3. This brilliantly illustrates that despite dropping 15% of its structural mass, the optimized wheel maintained a crucial safety factor of 3. That means the wheel can still handle 3 times its expected operational load before failing. So, the absolute uncompromising safety of the driver is still guaranteed. When you put the before and after side by side, the contrast is striking. You've got the bulky, heavy, solid conventional wheel rim on one hand. Compare that to the optimized, hollowed-out, power-generating mesh structure. It's lighter, it's way stronger, and it has the built-in capacity to carry the alternator system without adding any extra drag to the vehicle. It's a true feat of engineering.
Section 6. Future of sustainable wheels. And here's the best part. This isn't just a fun computer simulation. It has profound, real-world impacts on global sustainability. The researchers specifically highlighted the massive implications for developing nations. They noted that this generated electricity can easily be stored in batteries to provide power to areas without access to the national grid. Imagine the context of a country like Bangladesh. Cars equipped with these wheels aren't just saving fuel, they effectively become mobile, clean energy generators. They could potentially roll right into off-grid communities and provide much-needed electrical power to areas completely disconnected from traditional infrastructure. Which leaves us with a totally fascinating, provocative thought to conclude our explainer today. If a smart, calculated shift in wheel design, removing a little mass here, adding a pulley system there, can power a vehicle's electronics and potentially light up off-grid homes, what other everyday mechanical parts are just waiting to be reinvented? The possibilities of engineering optimization are truly endless. Thank you so much for joining me on this deep dive, and as always, keep learning.